Well, welcome, ladies and gentlemen. I'm Jim Ziegler. I'm the Executive Director of the National Iron and Steel Heritage Museum, so thank you for coming tonight. We'd like to thank our sponsors, first off, Peter and Ruth Nunn, the Stuart Houston Charitable Trust, Wegmans, and the Quick Stop Pharmacy. Tonight we will enjoy a presentation about the design, fabrication, and construction process, as well as the steel production process, which will speak to steel manufacturing methods and the development of bridge steel. Our presenters are Ronald Medlock from High Steel and Dylan Alexander from ArcelorMittal. So without further ado, I will introduce Dylan. Thank you, Dylan. Appreciate it.
All right, hi everybody. My name is Dylan Alexander. I work in the Customer Technical Services Department in ArcelorMittal, Coatesville. Our group is kind of a customer-focused group. We assist customers a lot with order entry. They'll come to us with new products and new ideas, and we'll kind of come up with solutions for them. And two of my primary duties there, I'm involved with our bridge steel, attending committees, conferences, kind of keeping in the loop with all our new bridge steel projects. And I also deal with customer claims, so when we have any quality issues, I'll travel out to customers and assist them to get through their problems and help find solutions for them. So I'm just going to talk a little bit about our Eastern Plate facilities here in Coatesville and in Conshohocken. And talk a little bit about how we produce bridge steel. So ArcelorMittal as a company, we're the world's largest steel producer. We have almost 200,000 employees worldwide in 60 countries. We're in all sorts of steel markets, whether it be automotive, appliance, commercial construction, infrastructure, with bridge steels. We have an R&D headquarters in East Chicago, as well as an R&D headquarters in Luxembourg. Just constantly trying to improve steel, make it better every day. We have mills and mines in 18 countries throughout the world. And as far as our worldwide steel production goes, 37% of our steel is produced in the Americas, North and South America. 47% of our steel is produced in Europe, and the remaining 16% is produced. We have mills in Kazakhstan, South Africa, Ukraine. So as far as our plate facilities go, we have our sister mills here in Coatesville and in Conshohocken. We also have a plate mill in Burns Harbor, Indiana, and then we have steel production facilities in Indiana Harbor and in Cleveland. They can melt steel for us. They're primarily what we call light flat roll, so they produce sheet product for use in automotive and appliance, appliances. Here's a breakdown of the capabilities of each of our mills. Our Burns Harbor mill has a 160-inch wide mill, as well as a 110-inch wide mill. They can produce plates as thin as 1/4 of an inch up to about almost 3.5 inches thick, and they're limited in the size of the slab they can handle on the mill. So their maximum pattern weight is just over 27,000 pounds. Here in Coatesville, we have two mills. The 140-inch wide mill, we can roll plates down to 3/16 inch gauge up to 28 inches thick. 130 inches wide and 75,000 pounds. And our 206-inch mill is actually the widest mill in the Western Hemisphere. We can roll plates up to 100,000 pound pattern weight and 195 inches wide. On this mill, we primarily just produce plates for the Navy, that go into the aircraft carriers, some large nuclear shielding, things like that. And then in our Conshohocken mill, they just have a single mill, 110 inches wide, and they specialize in producing lighter gauge plate. Here in Coatesville, we're thick and wide. Conchi produces plates only up to about 100 inches wide. They can roll coils up to 80,000 pound pattern weight, and plate thickness is a little below 3/16 up to about 2-inch gauge. I'll give you kind of the bird's eye view of how the steel's produced and moves through the mill, and then I'll drill down into each one of these areas individually. So over on the left here, you have kind of this is our melt shop area. So we have the electric furnace, we have the ladle furnace, vacuum degasser. Once the steel leaves the furnace, it'll either be cast into ingots or it will be strand cast into slabs. And then from there, once the slabs and ingots cool to room temperature, they'll either stay in Coatesville here and be rolled on our 140-inch mill or 206-inch mill, or we can move them over to Conchi and roll them at the Conchi mill. And then after rolling, plates can be heat treated at each facility, and then we'll ship them out to our customers. This is an overview of what happens inside the melt shop, and again, I'll kind of get into each one of these areas in more detail. So we have the electric arc furnace. We melt 100% scrap in here. Basically, what happens is we pile scrap in, and then there's 3 electrodes, graphite electrodes, that are lowered into the furnace to close the lid, and basically create an arc that will heat the scrap up and melt it. And then once that is brought to temperature, we'll move it to the ladle furnace. In the ladle furnace, we'll add some alloying elements if we need to meet a specific chemistry. We'll use argon stirring to kind of keep a homogeneous mixture there. And we can also calcium treat, that's what the wire feed is, and that'll come into play a little later on. Once the steel leaves the ladle furnace, it'll go to the vacuum degasser. Again, we'll keep stirring the molten steel with argon. Can add some more alloys if we need to meet the chemistry again. We'll basically run a vacuum through the degasser and pull all sorts of gases that we don't want in the steel: hydrogen, nitrogen, oxygen, because if we leave any of those gases in, it has the potential to create poor internal quality. You don't want bubbles throughout your steel. And then from the degasser, we'll either cast slabs or pour some ingots. So here's where the whole process begins, in the scrap bay. It kind of looks like a disaster area. But we actually do a pretty good job in the scrap bay of segregating the scrap. We keep alloy scrap with alloy scrap, carbon scrap with the carbon scrap, because we need to get the ingredients right when we're melting a heat of steel to meet the chemistry that we need to meet for our customers. So we control the scrap as we kind of build a heat, as we call it. And we balance out the scrap mix to create the chemistry we need to. So that scrap is then dumped into our electric arc furnace. As I said, if we melt 100% scrap, we're not like a blast furnace, so we don't melt coke and iron ore or pig iron. So 100% scrap, 100% recycled product. We melt 165-ton heats. Kind of sounds like a lot of steel, but as far as steel producers go, those are pretty small batches. So we have one of the more specialized melt shops in the country, and that relatively small heat size enables us to produce some very special alloy grades. We can make a plain carbon heat 1 hour, and then the next hour we're melting some aircraft alloy. So like I said, we're one of the more specialized melt shops in the country. And we can get, our productivity is about 100 tons per hour, so every hour and a half or so we're ready to melt a new heat of steel. And here is kind of a shot of what the melt shop looks like. I don't know, yeah, it's not going to show up well. But on the right here we have, this is the furnace. The lid is closed there, but the electrodes will be coming in the top. And then you see the ladle right there. And this is a tilting furnace with the tap on the top. So that is where the molten steel will come from. And when the heat is ready to be tapped, they'll actually tilt the furnace, and the molten steel will flow from that tap into the ladle. There are also bottom tap furnaces where they won't have to tilt it. It'll just the molten steel will just flow out of the bottom. So from there, once they tap the heat in the ladle, they'll take the ladle over to the Ladle Refining furnace. And here we'll deoxidize the steel and deslag the steel. That's basically taking out all the impurities, making it as clean as possible. Again, like I said, we'll add any alloying elements. Throughout this whole process, we're constantly doing chemistry checks to make sure we're meeting the chemistry we need to meet the mechanical requirements and the grade chemistry requirements. And then also the argon stirring and temperature control, just maintaining that temperature, keeping the homogeneous mixture of steel. From the ladle furnace, we go the tank degasser. The ladle basically is just put into a tank, close the lid, and put a vacuum on that ladle, and it extracts all the hydrogen, oxygen, nitrogen, things that we don't want in the steel. And that'll give us really good internal quality. And then from that vacuum degasser, we'll go one of two places. We can go to our ingot casting area, which you see on the screen here. Our ingots are bottom poured, so we have these sprues here. That is what the ladle will meet up with to pour the ingots, and then the molten steel will flow down that sprue and then fill these ingot molds from the bottom. That'll give us better internal quality as opposed to a top cast ingot. Top casting, you get some splatter, you can get some air bubbles in there, that reintroducing some air bubbles that you don't want. So this is the better option, bottom pouring. Our maximum ingot size produces about a 55-ton plate, and also we hot top our ingots. So you can see these boxes here. That's what's called the hot top. We basically overfill the ingot molds because as the ingots solidify, that molten steel shrinks up, and if you don't have a hot top, it'll just create a cavity on top. But that hot top, you have a little extra molten steel, so it'll fill any shrinkage cavities. Again, for better internal quality. The second place we can go if we're not casting ingots is we can cast slabs. We have a batch caster in Coatesville as opposed to a continuous slab caster like out of Burns Harbor Mill. So we, one heat at a time, we'll bring it over to the slab caster. On the screen to the right there, that's kind of what it looks like. You have the ton dish on top there. The ladle will pour the molten steel into the ton dish, and then from the ton dish you have your caster segments. So you'll start out vertically, and then as that steel moves lower through the caster molds, it'll start to solidify and run out the end, horizontally. We get about 1,300 inches or so of solid metal from one heat as cast. And we cast 9-inch thick slabs, 85 inches wide. Within the past 2 years maybe, we've gotten a 12-inch caster, which enables us to cast the thicker slabs, kind of take some of our load off of our ingot casting. Slab casting is much more efficient in terms of our yield and productivity. And our caster also has electromagnetic stirring. So we can actually stir the molten metal as it's solidifying in the slabs, which gives you better internal properties, internal quality. As the steel solidifies, all the dirt tends to settle in the middle, so that'll kind of spread that around and give you better quality. So from the melt shop, we'll take the ingots or slabs over to our rolling mill complex. Here we'll reheat the slabs up to 2,300 degrees Fahrenheit about. We have 15 of these reheat furnaces lined with refractory brick, just so all the steel they're made out of just doesn't melt. So ingots and slabs are loaded into those furnaces, brought up to 2,300 degrees Fahrenheit, and then they are picked with a crane and brought over to the rolling mill area. So our workhorse mill is the 140-inch wide mill. Has hydraulic gauge control. We can roll up to 28-inch thick plates there. About 130 inches wide is our max width. And this is the 140-inch mill pulpit. You can see on the screen there, there's two operators. This man's on the right. There'll be another gentleman to his left. And then they also have a foreman in the pulpit at all times, just managing, kind of making sure everything's going to plan. They have various screens in the pulpit, a bunch of cameras, kind of give them an idea, just so they can see what's going on better. It's a little tough to see when you're up in the pulpit what's going on down below. And they have a few screens that also tell them what sizes they're rolling to, what's coming up next, some gauge controls in there, force readouts from the mill, just to make sure they're not going to break anything. On the image to the right, that's a slab that's going through the mill. At the top right corner is where the mill rolls would be, and kind of in the middle of that photo, you see the two vertical rolls. Those are our edger rolls. So as the plate's passing in and out of the mill, we have the ability to use the edger rolls to produce a nice mill edge, and we can ship out mill edge plates as opposed to having to gas cut 4 sides of a plate. Our Conshohocken rolling facility, much different than Coatesville. It's a little more specialized to roll lighter gauge plates. They have a pusher furnace as opposed to in Coatesville we just have the furnaces where we just load them up, close the lid, get the steel to temperature, and then pull it back out. Here they have a pusher furnace, so it's set at the constant temperature, and they load slabs in the back end of it and just push them out one by one. As they keep loading in, they'll push slabs through the furnace. And they have 2 mills in Conchi. They have the roughing mill and then the finishing mill, which is a Steckel mill. The roughing mill will kind of just take a couple passes at the plate, get it down to a close enough gauge where they can get it in a Steckel mill. And then once it's in the Steckel mill, they have these 2 coiling furnaces on either end of the mill. And that's really helpful because with the lighter gauge material, it loses heat so quickly that if it cools down enough, they won't be able to roll it down a gauge. They can't exert enough force to get the steel any lighter gauge. So they will utilize the coil furnaces, and basically as the plates pass back and forth, they'll go up into the coil furnaces, keep the plates hot, and then roll it back through the mill the other way, and keep going until they get down to final gauge. And here's just why didn't that change? Yeah, there we go. So here's a picture of what that all looks like. You can see the 2 coiling furnaces here on either end, and then the Steckel mill right in the middle. So it's 110 inches wide, can roll plates about 100 inches wide. Again, hydraulic gauge control. They have the ability to shift and bend the work rolls, so they can kind of steer the plates as they're coming through the mill if they need to. They can roll down to about 3 millimeters thin, all the way up to 5/8 inch. They can produce coils that thick. Anything thicker than 5 inches will just be discrete plate, which means they don't utilize the coiling furnaces. They just roll it back and forth, similar to how we would produce them in Coatesville.
Are they still using? Are they using 120 mil still? Or they're...
No.
So it's sitting idle there then.
The 120 mil.
They brought it out of here, took it up to Conshohocken.
Oh, is it still there?
Yeah.
Yeah, definitely not using it anymore.
Sorry.
So, yep.
Skip, you can get it back now, huh?
Yeah, I guess I don't know.
And they also have edging rolls to produce mill edge plate, so we don't have to gas cut all 4 sides again. And here's kind of what that all looks like. You can see if they're rolling in Steckel mode, they have these flaps that come down, and that guides the plate back up into the coiling furnaces. If they're rolling discrete plates, those will just be left up, and the plates can pass back and forth freely. They also produce what's called K-coil there too, which is when they utilize the coil furnaces to keep the plates hot as they're rolling, but on the final pass, they'll just let the plates come through and roll out flat instead of letting them cool in a coil. When Conchi does produce coils, you can see one sitting right there, and there's one on the spindle there being unraveled. They can produce light gauge plates in a coil, let it cool, and then process them on the shear line, or cut to length line, I'm sorry. And here basically they have a leveler, and they'll uncoil the coil, pass through the leveler, and that'll flatten the coil out, take out all the memory, and then they'll just cut it into more manageable plate sizes that we can truck or put on rail cars. Here's a little overview of how we may process steels, especially bridge steels. Certain grades of steel require a higher toughness and higher strength, so we can heat treat them in Coatesville and Conchie. So to the far left, this is kind of the process that a normal as-rolled carbon plate would go through. You know, heat it up to 2300, take your rolling passes, and just let it air cool. And that's going to produce, you know, fairly average strength and toughness. But for certain grades, you want them stronger and tougher. So two of the primary heat treatments for bridge steels, you have a normalizing, which is where you heat plates up, not quite to rolling temperature, but about 1650 degrees Fahrenheit, let it air cool, and that'll give you a very uniform microstructure, very tough steel. If you want strength and toughness, you can do what's called a quench and temper. Again, heat the steel up to about 1650 Fahrenheit and just dunk the whole plate in water. But what that's going to do is create a very brittle plate that's going to fracture. So what you want to do is soften it up a little bit, and then what that's called is a temper. Heat it up slightly, maybe 1100, 1200 degrees Fahrenheit, and then just let it air cool. And that'll give you a very strong and tough plate. To the right there, TMCP processing. Our Burns Harbor mill can do that. We don't have that ability in Coatesville or Conchie, but that can be used to produce some bridge
So
steel.
they're still in
grades as well.
operation at Burns Harbor?
Yep.
Are they?
So here's our heat treat facilities, some details on that. In Coatesville, we have the continuous furnaces, which are roller bottom furnaces. We have a 200-foot long and 145-foot long furnace with a platen quench in the middle. So if we want to do a quench and temper, we can put plates at one end of the furnace, they just roll through, and then the platen quench will clamp it down, keep that plate flat, and we'll spray water on it to cool it down as quickly as possible to give us the strength we're looking for. For heavy gauge plates, we have our batch heat treat facilities. So we have these car bottom furnaces. You can see one on the top right there. We'll place plates in the furnace on ceramic piers, close them in the furnace, let them heat up, and then once that plate's red hot, we'll dunk it into a giant pool of water. And that'll quench it, give us the strength, and then once it's down to room temperature, we'll pull it out of the water, temper it, and that'll soften it up and give us the properties we're looking for.
Is the furnace gas?
Yeah, all our furnaces are natural gas. In Conshohocken, we have a roller Q&T line. So as opposed to Coatesville, where we have the roller furnace and then the platen quench, where the plate's just stationary, in Conshohocken, they can actually continuously roll the plate through, heat it up, roll it to the quench, roll it to the temper, and then the plate just pops out the other end, ready for final testing and to ship after that. And they also have 2 normalizing furnaces. They can do the normalizing heat treat if they don't want to quench and temper. So we'll talk a little bit about bridge steels. There's 2 main societies that do a lot of the bridge steel promotion and kind of spec writing. There's the American Iron and Steel Institute and the National Steel Bridge Alliance. So AISI is focused on steel promotion in all industries. That can be construction, mining, infrastructure. Their goal is just to get the word out on steel, promote it, write specs, all sorts of stuff like that. Do some they're involved with research through universities. The NSBA is more strictly focused on just the promotion of steel use for bridges. So steel producers and fabricators and designers, members of academia will attend NSBA meetings. And they'll also they'll work on writing new specifications, revising design codes, and promoting steel versus concrete out there in industry. So this is where a lot of the work takes place, just in developing steel and promoting it. So some of the benefits of steel and bridges, it gives you a lot of design flexibility. When you precast concrete, you're kind of limited to the sizes and shapes you can make, but with steel you can weld it, you can cut it, you can bend it, you can do a whole variety of things, make all sorts of different shapes. So very flexible, easy to use, gives you a lot of design options. You can paint it, leave it unpainted if you want, depending on what grade you're using or what your environment is. You can also inspect it in the shop and in the field. All these girders are made in a shop. It's much easier to inspect as opposed to building a concrete bridge out in the field where it might be much more difficult to get eyes in certain areas and much more costly to inspect. And similar to the flexibility, it can be used in challenging applications, making all sorts of curved girders, different shapes. If you have low clearances, you can modify your design, maybe use a higher strength steel versus a lower strength steel. And you also have lighter weight structures to transport. You can carry, one girder at a time into place. You don't need to necessarily build a whole section of a bridge and lift it, but sometimes that also has its advantages too. So there's two main organizations that kind of govern bridge steels. You have ASTM, the American Society of Testing and Materials, and AASHTO, which is the American Association of State Highway and Transportation Officials. And then the two main governing specifications are ASTM A709 and AASHTO M270. And this kind of provides bridge designers and fabricators with kind of off-the-shelf products that they can use every day. So all the testing requirements are laid out, all the mechanical requirements, all the chemistries. It's all there in those two specifications. And there's a couple, here's a couple of grades that are detailed in those specifications. You have some just carbon grades. These grades are all characterized by their minimum yield strength requirement. So A709 grade 36 would have a 36 KSI minimum yield strength. Grade 50 would have a 50 KSI minimum yield strength, and so on. So grade 36 and 50 are your as-rolled carbon type steel grades. Then you have weathering grades, grade 50W. High performance steel grades, 50, 70, and 100W. And then we also have a newly added, it's called 50CR. CR stands for corrosion resistant, so it's actually a stainless steel.
I'm sorry, STAR stands for what?
Corrosion resistant.
Oh, corrosion.
Yeah, it's stainless. And in those specifications, you have one of the big things in there is they have the guaranteed impact strength requirements all automatically laid out. So zones 1, 2, and 3, depending on where you're building your bridge in the country, that'll determine your toughness requirements and what kind of temperatures the bridge may see in service, because the colder the temperatures, the more easily a bridge is going to fracture. So here's just some of the sizes we can produce in Coatesville and Conchie. The top is kind of like where grade 36 is. That's kind of if you want maximum gauge, maximum width, we can roll a 624-inch plate. If we're just going for maximum length, we can roll about a little over 1,500 inches, 1-inch gauge, 84 wide. So that's just kind of an overview of our capabilities. So a little bit about weathering steels. These steels have small alloy additions, just copper, some nickel, molybdenum, and chromium. And what that does is it helps the steel resist corrosion. So as we all know, steel rusts very easily, but these they develop what we call patina. Looks a little rusty, but it's a patina. And they corrode much more slowly than a traditional steel. So you can set it out there unpainted, and it'll perform just fine for years and years. This is all of our high performance steels are also considered weathering steels because they do have those alloy additions, and they are more corrosion resistant than a traditional carbon steel. But these weathering steels are not suitable for seaside applications. You don't want to put it right by the beach or maybe up north where they're going to seal out of road salt. We would recommend that you would still paint a weathering steel bridge in those conditions.
Where are you getting your additives? Where?
So we do, since we melt 100% of scrap, we do get a fair amount of copper and other alloys in the scrap we melt every day.
Okay.
If we need to add any raw alloys, we can, but generally speaking, we control the scrap well enough that we can hit the chemistries we need to by just, recycling scrap. So.
Really, you don't have to import.
So how do you know what the scrap is made of? I mean, you're getting scrap
Yeah,
all over.
yeah.
You say you're separating it out, but then how do you know what it is? It
Yeah.
doesn't come with a tag on it.
You have to have trustworthy scrap vendors, because you can have scrap vendors that say they're selling you one thing but it's really not. So you kind of have to have a good relationship with them, and know that you're getting what you're paying for, because on the opposite end of the spectrum we have grades that we don't want a lot of residual alloys in. We want low copper or low nickel, so we have to trust that they're giving us that scrap.
Okay.
But you can test it in the melt, right?
Yeah, throughout the whole melting process, we're constantly doing chemistry checks and just verifying where we need to be. So,
How long would you anticipate a weathering steel bridge to last?
good question. It depends a lot on the environment it's in. Maybe Ronnie, you might know this one better.
Yeah, I would say it does depend on the environment. I used to work in Texas, and we did a study of our weathering steel bridges, because we had a lot of debate. And as surprise fight, and as Dylan said, the steel forms a patina, an oxide layer. So we looked at 30 bridges, and we found only one that actually had the oxide layer yet. They were corroding so slowly. Now you think Texas is dry, but a lot of these bridges were in Houston, where they get 60 inches of rain a year. Of course, there's not a lot of salt used there. But it was pretty obvious to us that these bridges would last as long as you would need. 100 years is not going to be a question. In fact, you would even see mill scale. Some of these bridges were 30 years old, and the mill scale wasn't even off of them. So unless there's something that is compromising it, like saltwater spraying on it, it'll last forever, in my opinion.
And here I'll talk about how we've developed our high performance steels. We started developing them in the mid-90s, and I'll just go through a little bit of the driving factor of how we came to the high performance, steel characterization. So first off, sulfur in steel is generally considered an impurity, but throughout the years we've been getting better and better at reducing the sulfur content in our melts. And then in the 70s, we came up with this fine line product, which is calcium treated steel. Like I said earlier when I was talking about the melt shop, we add calcium wire into the melt. So what that does is it kind of bonds with the sulfur and makes these, these globular sulfides. And I'll show you coming up in the next slide here. So this is kind of a traditional sulfur containing steel. You see you get these stringers in there, and those are really good places for cracks to form. So you reduce the sulfur a little bit, you get, the sulfur is a little more scattered around throughout there. But then once you treat it with calcium, you get these nice little balls of inclusions as opposed to, the long stringers. And it's much more difficult for a crack to propagate when you don't have these long, sharp inclusions in the steel. So our HPS steels are alloy steels, calcium treated, low sulfur, so very high toughness, very high strength. And not that this is very important, but these are impact results for HPS 70W, so 70 KSI yield strength. And if you're not familiar with an impact test, we basically mill a little bar of steel in the test slab in the mill. And we basically drop a hammer on it and measure how much energy is taken out of that hammer as it breaks through the steel. So, spec minimum is down here at 25 foot-pounds, and those are our averages for a whole lot of samples of impact strength for
Where do you do
high-performance
your
steels.
testing now? Because you don't have the test lab down on the other side of Coatesville, do you?
Yeah, it's right off Route 30, the test lab.
Right here in town?
Yep.
Oh, you still have that one open?
Mhm. Yeah.
Okay.
Yeah, we do all our in-house. Almost all of our testing is still in-house. So,
So
yep.
high-tech testing is dropping hammer on.
it's a little more high-tech than that, but yeah. So that gives you an idea of how much tougher, on average 6 times more tougher than the specification minimum, and that really gives steel fabricators, bridge designers a lot of confidence that their bridge isn't going to fall down on them. So it's always a good thing. So when is HPS used? It's more costly than a traditional bridge steel, so they have hybrid designs. In an area of a bridge that's more highly stressed, they may substitute HPS for, instead of using a traditional steel. Or in fracture critical applications, a bridge is deemed fracture critical if a member of the bridge were to fail, the bridge would fail, collapse. So in those types of fracture critical designs, it may be beneficial to use an HPS steel. And they're used to reduce weight, girder weight. You can use shallower girders, maybe thinner cross sections with higher strength steel instead of making a really heavy, beefy girder. And I know a lot of HPS steels went into the Tappan Zee. So,
What's an example of the high stressed areas?
any sharp corners. If you're kind of mid-width on or mid-length on a span, and you have a lot of deflection, you're going to see a lot of tensile strength there. So, here's a rendering of what the Tappan Zee Bridge is going to look like. It's actually almost completed, I believe.
Governor Cuomo.
Yeah, the Governor Cuomo Bridge. So
One span is up and in use.
yeah, the
That's what
one
the
is
other day.
right.
One is,
So at ArcelorMittal, we produce 160,000 pounds of steel going into this bridge. Tons. Yeah. That'd be a pretty small bridge.
So repeat that again.
Yeah, 160,000 tons.
Sorry, Dilly, good enough.
Yeah. About 60,000 tons went into the pilings that were produced at our Burns Harbor mill. But all of the plate that was produced for the girders was produced here in Coatesville and Conshohocken. That's 100,000 tons.
So,
get it up there.
let me pick your brain about that design. Is that better than a standard suspension bridge? More flexible, more durable?
Are you going to touch on this, or do you want to?
Okay.
I'll talk
Okay.
on that.
All right.
Yeah.
I'll wait.
And then we also, after innovating the HPS steels, we've also have this new product. We call it Dura Core. Its ASTM designation is A1010. It was recently added to ASTM A709 as grade 50 CR. So now it can come, ordered with all those standard bridge testing requirements. And it's actually technically a stainless steel, 12% chrome. Very good corrosion resistance. Definitely doesn't need to be painted. Weldable and formable. We can produce plates in this grade down to 3/16 of an inch, up to 2 inches right now. We've actually just greenlit producing it up to 3 inches. So that should help us out. Customers can build, thicker girders if they need it. And it's sold in 2 grades. We have the 50 KSI yield strength grade, or we can sell it to a hardness. It can also be used in wear applications for lining coal cars, dump truck beds, things like that. And here's some images. The Brandywine Creek runs right through the mill. So we built a Dura Core bridge over the creek, built by High Steel, I believe. So those are some girders there. That's it in construction. It's not a typical looking stainless. It doesn't look like your refrigerator at home, nice and shiny. It does get this rust color to it, but that's the patina, and that's that oxide that forms that really helps the corrosion resistance. And here's a brand new bridge that was just finished up in Ontario, Canada, over the Highway 401. They use a tub girder design, not a typical eye girder, but obviously they use a lot of road salt up in Ontario, so it was beneficial for them to build this bridge out of stainless as opposed to a carbon steel. And here's a couple resources we have. If you want to look up any more information, we have our website, ArcelorMittal.com/plate, and these two brochures are up there. Our plate spec guide is basically a catalog of all the steels we make, and then our fabrication guide is very useful, for all sorts of welding, cutting, cold forming, things like that. I don't know if you have any questions for me? Yep.
I very recently read an article about China and their steel production, and it mentioned in there that they produce more steel than the next 4 countries in the world combined.
Yeah, I believe.
Did I read that correctly?
Yeah, they have a very big overproduction problem in China, and I know they've been trying to scale it back, but one of the main issues I think is their steel mills are subsidized, so they can sell it really cheaply. They can sell a lot of it. They need a lot for their own infrastructure needs in China, but they also do dump it over here pretty cheaply as well. So
I'm curious why the containers that the molten steel goes into doesn't melt.
they're all lined with refractory, so ceramic type bricks. Those do wear, and we do need to replace them on a periodic basis. Sometimes they wear more quickly than we expect them to, so we have what's called breakouts, which is, you have a hole in your ladle and it leaks out on the floor. So that's never good to avoid, and we kind of plan maintenance so that doesn't happen.
Sometimes at night there's a huge bang and the whole earth shakes. And I just wondered what causes that bang.
How close are you?
Somebody drops something. I'm up on 5th and Chester.
What could that be? It could be a plate dropping. I doubt it'd be any
It's
sort
not
of.
when it goes through the roller, like boom, through the roller.
Yeah, it can be pretty noisy in there. Yeah.
I
Yeah, if
don't
it's
hear it too much because I'm quite a long way away. But
yeah, if it's
every
quiet
now-
enough, you could probably hear it. Yeah.
Every now and then you get a real clang.
Mhm.
And I think, is it really somebody dropping something? It's not.
Yeah, it could be, depending on how loud it is. I mean,
Shut that hammer.
yeah, the melt shop's a noisy place all the time. The mill can get noisy if they're rolling. So.
Right, it's probably wrong.
As you know, we used to have 3 electric furnaces at one time, A, B, and C. And I guess one of the things that I was interested in now with the one furnace, we now have it so that you can take those apart and actually have others standing by to put together again, hook it up, wire it up, whatever. And that seems to be very efficient.
When you had 3?
We had 3 at one time.
Yeah. Now we only have the one. I guess it was during the summer. We had to rebuild the foundation, so it was down for almost 2 months.
Yeah, we had 3
So, yeah.
150-ton furnaces
Mhm.
at one time.
Yeah, so when we go down,
No, it's very
It's a
efficient the
problem.
way you're doing it now.
yeah, I mean, I've heard that we can produce the same amount of steel we always have, just with the one furnace. So
So what's the weekly tonnage?
weekly tonnage. We can. I don't know all out how much we can produce. I will say on a monthly basis, it's these days running in 20,000 tons, give or take, a month.
How much more steel do you have to melt and roll for the Tappan Zee, or is that pretty much done?
That's all produced.
That's
yeah.
all. That's
Yep.
all produced. You have any more bridges on the line?
Constantly, yeah. I don't think as many. Obviously, that's a huge project, so
course.
nothing with that kind of press around it. But we sell bridge steel all
I
day.
was thinking of
so-
highway bridges with the new administration now coming up
Yeah.
with some more highway building.
Yeah, I don't, that's the hope, that they pass some good infrastructure bills. I don't know if anything substantial has been done yet, but that's our hope.
Did all of that steel for the Tappan Zee, was that shipped up by truck? How did it get up there?
Yeah, the girders were actually fabricated down in, by High Steel in Hirschfeld in North Carolina, and High Steel in Lancaster and Williamsport. And either trucked or barged.
Who's your competition quoting against you for the steel for that bridge?
For that bridge, domestically, well, I can tell you, I think it was, and Ronnie probably knows. Our big competition domestically is Nucor and SSAB. So I don't know that they can produce the range of sizes we can produce, so maybe why we won the bid. But
I got a question about the squashed cars.
okay.
I noticed after Hurricane Sandy, there was a gigantic pile of them. And I always wondered, before they squash them, do they take out the plastics and the upholstery and the engine and that, or does all that get melted in the furnaces?
I think they could. I actually heard a funny story a couple years ago when they did the whole cash for clunkers deal, that they were having issues with a lot of lead in steel, and it was causing them a lot of problems. And they were doing chemical analysis, and they said, "Oh, our lead levels are off the charts. Where's it coming from?" And they said, "Oh, it's probably from all the junked cars they've been melting, and they don't realize that it's in there and that it's a problem." So I don't know how well they dismantle those cars. I know I've seen some of them that have they look pretty intact. So, but whatever impurities are in the furnace will boil off, and we'll capture them. So
Would we be getting any squashed cars from Florida and Texas?
it's definitely possible. Yeah, they have to go somewhere. So
When you make a boilerplate, do you roll it into the shape of of the destinated boiler, or does the
no, actually, these days we only produce flat plate. So I know in years past we did some manufacturing here, but yeah, these days we just roll flat plates and ship them, and then that's up to the fabricators to form them.
Is
We
there
heard a lot about the bridges that they've been reassessing and replacing. Is there a numbers on how much were related to steel defects versus a concrete, or?
I don't know if there's been any studies done. As I can tell you that I think steel is much more has much more longevity than a concrete bridge. I think you can probably agree. But I don't know if there's been any studies really done on exactly how much longer.
I noticed there was a letter floating around somewhere saying that they were going to shut down the melting facility in Conshohocken.
They're idling the rolling mill.
Idling.
Within
That's
the
better.
year.
I like that term better.
Yeah. So yeah, with the 110 mill in Conchie and the 110 mill out in Burns Harbor, I guess we have a little bit of overcapacity for that size.
Oh.
So they're going to idle the Conchie mill, and if things
Won't have any effect here.
no, it should not affect most of the products we produce. So they're going to idle it and bring it back up if business permits.
Right. Should.
So if how was that bridge fixed, the Turnpike Bridge?
So what happened there is it had a plug weld put in. They misdrilled a hole, put a plug weld in it when they were fabricating it, and what that does is there was a heat affected zone around that weld. It caused the steel to kind of become a little weak in that area, and then over the years, just with the constant load up and down, it finally gave way. And I believe they just jacked it into place and bolted splice plates around the outside of it to hold it there.
All right, folks, we're going to switch presenters here, and if you have other questions, feel free to ask them at the end here. So.
Good job.
Okay, how are we on time? Any concerns?
Got an hour.
It's getting late. I could go a long time, or we could do it in 10 minutes. Let's see.
Almost 7. Half an hour?
Half hour? Okay, I'll try to go quickly then. My name is Ronald Medlock. I'm with High Steel, right up the road. I've been with High Steel since 2006. I'm originally from Texas. I went to the University of Texas and then worked for Texas DOT. So I worked on the highway DOT side until 2006, and then I came up here to High Steel. So I'm going to tell you about the Tappan Zee Bridge. First, a little bit more about High Steel. And you can kind of see the map here. You guys are here. We're out in Lancaster. I'm sure most of you know where Lancaster is. And if you get out there, let's see, we are, oh, that mouse is a little gimpy. Yeah, we're right here where the dot is. And this is that zone where all the outlets are. So if you get up to do the outlet shopping, and you go right around the corner to Old Philadelphia Pike. We're right on the corner of 30 and 340. If you drive by, you see a lot of great looking girders in the yard. We've been going since 1931. Sanford High bought High Welding, bought the welding company and started it then. Since then we've grown to all these other companies, High Concrete, High Real Estate. If you drive around Lancaster County, you see a lot of the High Real Estate signs, and they're in hotels and everything else. But the original company was High Steel, and we do have plants in Lancaster and Williamsport. Our market area is primarily Maine down through Virginia, and basically we'll build a bridge anywhere we can win the bid. Girders, which is our primary product, it's difficult to be competitive very far because there are a lot of girder fabricators around the country. But there aren't that many who do the specialty stuff. So for example, we did this Milton Madison truss over here across Ohio. We recently completed a truss in Missouri. We did another one in Nebraska. So there's not that many people who do trusses, but a lot of people do girders. There's a bridge we did in Ohio, some other examples. So a lot of bridge fabricators only do girders, and then there are a few that will do just about anything, and we're one of those companies. So here's some examples of some of the stuff. Like you see this truss, you might recognize it if you take 76 into Philly here on the left. Tub girders. This is Phoenixville. Arch bridges. Cable stay down in South Carolina. And there was a question about this type of bridge. These days, if you look at those big crossings, what you're usually doing is covering a shipping lane. And for a shipping lane, you need about 1,200 to 1,500 feet. And if you look at a design, a cable stay gives you a pretty good efficiency in that range. If you get up into the sort of mile range, even half-mile range, suspension bridge starts becoming more economical. Another thing that's a lot of designers like these days about cable stays is there's a lot of redundancy. If you lose one or two of these cables, that's not going to be a problem. If you have a suspension bridge and you lose a suspender, well, your bridge comes down. It's fracture critical, right? That's not the driving reason they go for it, but these days, any of those 1,200, 1,500 foot main spans, you'll get a cable stay. So we did that one in South Carolina. Here's those are our arches, trusses, but the number one thing we do is girders. One thing that is interesting to note in terms of the evolution of bridges, it was really welding that changed bridges so much. It's probably the biggest revolution in bridges in the past couple of centuries. Because if you think about before welding, what we did was a lot of smaller, stubbier things that were riveted. And riveting takes a lot of time, it's very costly. And you'd put a flange on a web with some angles, you put holes in everything, and then you get guys putting those rivets together. It was very difficult to do curves. I don't know that you could really do a curve with a riveted structure. But if you look at welded bridges, you know, you can pretty much do anything. You saw those arches, you know, you just cut the plate to what you want, you fit them together, curves. If this is an interchange north of Baltimore. You know, we all love those direct connectors. You know, think about the old days, right? Interchange with that lights. These days you fly through there at 75 or 80 miles an hour. And you can do it because of these nice long spans, steel bridges that you can make because you got the plate and you can weld them. So it's worth noting, that welding. Our capacity, we build about 200 bridges a year. Not all of them Tappan Zee size, of course. If you think about most of the bridges you see out there, they're grade, separation, you know, overpass, underpass, couple of spans. They might have 20 or 30 girders. So that's about 200 a year.
Are you doing that one on the turnpike between Norristown and the Delaware Bridge? There's a connector, it looks like it's.
Yes, yes, we are doing that. And we also did you know, Dylan was talking about the bridge that broke. We supplied those plates to fix that as well. Smaller project, but kind of interesting.
It's important.
Yeah. So 14 girders a day, 40 cross frames a day. If you look at a typical bridge, it really comes down to a couple of things: the girders and the frames, and about 40 frames a day, and then about 60,000 tons a year. Okay? So that's the number Dylan likes, because it's almost all plate and shapes. You see, we use shapes here in these frames, but most of the stuff is plate. Around 617,000 shop man hours a year. So we have about 450 people who work in our shops building bridges.
Those
Yeah.
pieces are welded together?
Which ones? All of them, yeah. Well, like here you'll see there's some T's making these frames. So here's a gusset plate, and that's plate, and then here's T's, and there's plate there.
What about the girder?
The girder is all plate, yeah.
Pieces all welded together.
Yeah, yeah. So what we do is we cut these webs, and we cut these flanges. And, you know, so this web was cut to that shape. And now it's upside down. That's a haunch bridge. Okay, so you know, some of them have got the haunches. Some of them are what we call parallel flange. We cut the webs to the shape that's required. We make these flanges, which are thicker, and then we weld them together. So we have a lot of these long welds. If you're familiar with welding, we use submerged arc welding, probably 80 or 90%, because you get a lot of deposition from submerged arc welding. These plates here typically will have butt splices, because they're only so long and they change in thickness to give you design efficiency. So there might be a weld here and another weld there. Also, these plates, Dylan can make them very long, but they all arrive by rail at our shop. And 90 feet is about the limit before you're going to multiple cars. So usually that's about what we get as a 90-foot plate. Most girders are 120, 130, 140 feet long. So we're splicing webs and we're splicing flanges to make those girders.
Do you do a lot of that business on the New Jersey Turnpike when they put those truck
Yeah.
lanes in?
Yes.
Yeah.
Yeah. Our biggest. We are the probably the largest fabricator in the country. Our biggest competition is Hirschfeld, and Hirschfeld does a lot of that work up there too.
Oh.
I'm gonna say we probably did about 2/3 of it, and they might have got the other third. Yeah. So onto the Tappan Zee Bridge. Dylan mentioned it. And from your discussions, the comments, I can tell some of you guys have been up there and you've seen it, right? So the Tappan Zee is up here on 278. And if you think about the traffic moving through this area, if you're coming from...
287, sir.
Oh, sorry, 287, thank you. I don't mind the corrections, but...
Those type.
Yeah. It's probably right here on the map, isn't it? You could have read the map. 287, thank you. Yeah, so traffic, no, yeah, 278's down here. It's on the map too.
Staten Island.
That's a Verrazano down there.
Yeah.
So, you know, all the traffic moving between the mid-Atlantic and the Northeast pretty much has to go through this area. I mean, you can go up and around.
Oh, yeah.
But if you're going to go through the New York area, you can go through the city on the tunnels or the GW, or you can bypass that on the Tappan Zee. So there's a lot of traffic that gets up there and goes in that direction. I've got it circled. Interesting thing, the Tappan Zee Bridge, kind of a good thing, is at the widest point in the river. Anybody have any guesses why? You know why that happened?
Is it slower?
Slower? No?
They wanted to get shipping up to Albany and back, I think.
Yeah, no, it's an interesting story. It's a nice political story.
Okay.
Yeah, you know?
I think the Port Authority was to be avoided, so they built it north of the city, so they wouldn't have to deal with the Port Authority.
Yeah, it's generally, yeah, that's about right. So the Port Authority of New York and New Jersey has jurisdiction on all the tunnels and bridges into the city
Right.
from the Statue of Liberty, which is down here, on a 25-mile radius. Okay, so this bridge, the Tappan Zee, or the old Tappan Zee, was owned by the Thruway, and the Thruway wanted to get as close to the city as they could. So if you go 25 miles from the Statue of Liberty and a few feet, you come to the. So you were right on track. Yeah, and of course, what they wanted was to get as close as they could, so they could get the toll revenue, right?
But not in authority.
So good news for us, long bridge, 3-mile long bridge.
Is that what it is?
Yeah, so that's really pretty cool. We, as Dylan said, if only we had some more of those.
Is that one almost completed, that one section?
Yeah, and I'll get to that. I'll show you something. Okay.
Yeah, one span is done in use.
Oh, really?
Yeah, I was up there Saturday.
Yeah.
Yeah. So this is not the Tappan Zee. This is a bridge, the one we did in South Carolina, but it shows you the kind of things that are going on. This bridge was done in the 20s, this one in the 50s, and then this one is in the Ravenel Bridge in the early 2000s.
Wow.
So what you'll see is how the approach spans change. And you know, remember I was saying the old bridges used a lot of small parts riveted together. So you know, what could you do then versus what you can do now? A big factor on these approaches is that substructure is very expensive. And it's gone up exponentially as environmental sensitivity has gone up and as labor has gone up. So when you're building a bridge, you want to try to put as few piers in the water as possible. Of course, the newer spans, these are 175 feet. And so these were, golly, I don't know what they were, 30, 40, 50 feet, okay? Lots of piers in the water. Of course, in the old days, you used trusses to get these spans. When they replaced these two bridges, and they're gone now, you see they went up much higher because ships, that's a shipping lane, and ships have gotten taller. So they added that shipping capacity when they replaced that bridge. And the same kind of thing, as I mentioned before, that cable stay around 1,200 feet to give you a nice wide shipping lane. But that's all you need at elevation. The rest of it can be closer to the water. So like the Tappan Zee, you know, it comes back down. So the same kind of thing that was going on in the Tappan Zee when they replaced it. So a couple of high-level things. The budget for the bridge was $5 billion. Came in at 3.9. It's actually right now at 3.98. It's the largest project going on in the United States, single project. And you know, it's a very nice testament to what we've done. ArcelorMittal, High Steel, the Tappan Zee constructors, because a lot of these big mega projects don't come in on time and on budget. You know, it's not unusual to see them go 2-3 times. You read about it in the papers, right? There's a bridge in San Francisco as an example of Oakland Bay Bridge that, you know, the original bid was double what they expected, and then it was late and it was double the cost of that. But Tappan Zee has come in on time and on schedule, so that's really very good. They're highly concerned about durability. You know, they don't want to get back out there. One of the things the owners face these days is that they don't have money to send people out to do maintenance, and of course they don't want to be replacing the bridge. Keeping the existing Tappan Zee Bridge open was costing them millions every year. So that was what was driving them to replace it. And what I understand, I've heard, they built it sort of quickly. It was built in the 50s. So it really isn't a very old bridge. I mean, we have a lot of other older bridges. You think about Golden Gate in the 30s and the Brooklyn Bridge in the 1880s. But they really, you know, it wasn't executed very well, and it was costing them a lot to maintain it. So that was a key driver for retaining it. So they were looking at trying to get a 100-year life. There's a lot of debate on the coating. They ended up with a 3-coat paint system. These two products, when you buy primer, it's either organic or inorganic. We like organic because it's faster in the shop. The inorganic, you have to wait for it to cure. So we were in a lot of discussion with them about that, and we told them, if you want to maintain that schedule, you need to go organic. and they did that, so that was helpful. Foundations were a very significant cost factor. Dylan mentioned the pipe piles. You see them here. They drove the 6-foot diameter pipe, 1-inch wall. You know, I don't know how long those sections are. Maybe they're 80 or 120 feet. They drive them down. They had to use these special bubbles because they were concerned about the noise impacting the sturgeons that were in the room.
And the people.
Yeah. So you see the guys here. Lots of field welding. Okay. They would drive that section down, bring another one, weld it, 1-inch weld, drive it down. At one point they had 45 guys out there welding.
Oh my word.
Okay. And these pipes are sacrificial. They are there as a form for the concrete that's inside. You know, you'll notice they're not coated. But the guy who designed it said, yeah, they're anticipating losing about 3/8 section over the first 100 years of that bridge, but it's not a problem because it was really just a form. Okay. So the main span is cable stay, and then the approaches 350 foot with long spans with 12-foot deep girders. So I'll talk in a little more detail about that. You see here the construction going on. You once again look at the old bridge and look at the span lengths. Those are 80-foot spans. So think about how much substructure, how many piers are in the water for that old bridge versus the 350-foot spans on the new bridge. Okay. Now there was a design competition for the new bridge, right? There were first 4 and then 3 teams that went to compete. You had that main span, but then you also had 3 miles worth of approaches. So the teams that were bidding on it were looking at, well, what is the best way to accomplish the approach? And so the designers, you know, they're keeping their cards close to the vest, right, because they're competing. But they would talk to us and say, well, what size should we go? Because with a span, the distance you go is the span to depth ratio. I think I have it here. Yes. Okay. So if you look at a typical bridge, you'll see the girders are so deep. The longer you go, the deeper you need, because that bending is a question of the stiffness. Okay. So the designers realize that they can go further and further and further with deeper and deeper girders. So they were talking to us and other suppliers. Hey, how deep should they go? We've done as deep as 14 feet. Dylan was talking about that mill, 296 or 200 inches, something he said. So we did a bridge in western PA that had 14-foot deep girders. 14 foot, I mean, that's like almost a 2-story house, I mean, right? I mean, that is really deep. But it was, the costs start to go up exponentially as you get to that higher height. And so we said, well, we looked at it and you ought to go 12 foot. Are any guesses on what is the key factor that took us to 12 feet? Anybody? I'll tell you. Shipping.
Shipping?
Yeah, okay. Because you think about it, you know, we could make a 14-foot girder. We've done 17 or 18. But it becomes very difficult to ship and very difficult to deliver. But we told them, you know, if you go to 14, you could go to 400, but the cost to ship is really going to go up exponentially. We recommended a 12-foot deep girder, and so that was what they went with. We prefer to ship the girders standing up. That way we don't have to lay them down. That way the contractor doesn't have to turn them. We can't always do that. Anybody know what the limiting factor is there?
The bridges they go under.
The bridges we go under, that's right. Whenever we get a job, we look at, and you know, we get up there, even a shallower girder. We'll look at where is it going, and our transit guys will figure out, can we go under those bridges? And of course you can't trust the published numbers, right? Because all they have to be is a little short and you're a little tall and you're done and you're replacing a bridge. So our guys will, no matter the job, they'll get in a little truck and they'll drive their route, and they have a thing they put on the back to make sure that it's not going to hit the bridge, right? So we, you know, preferably would ship like this, but we couldn't do it on Tappan Zee, but we could do a 12-foot
Yeah.
Why can't you do a 7 and a 7 on top of each other to make 14?
Yeah, you could, but if you do that and you send them to the field, now you're adding field work, and they're trying to minimize that. Okay, so they could. And in fact, we did a bridge near Pittsburgh that was 530 feet, and it had haunches at the piers, you know, that came down to a haunch and came back up. And here they were 18 feet, but there were 2 pieces there, and they had to bolt them together. It gets fussy. Okay. So,
So you don't do strength, you can do that.
oh, you could. Oh, yeah, I've seen 23. Okay. But it's, you know, how do you get it there? Right. And for us, we start running into capacity problems too. If how tall is our shop, how big are our cranes, things get heavier and heavier. Okay. That's the other thing is that the deeper you go, the heavier your bridges get.
When would you travel with a load like this? At night or something like that? I'm just trying to think.
Yeah, it depends on the rules, and it's funny because PA is day only and New York is night only for some loads. Yeah, it gets to be an issue. Yeah.
That's huge.
One of the things on this job was the super loads. Okay. Now, everything we do has got a special permit. Okay. They're all permit loads. But some of them are super loads. And a super load means that you have to have police escort. Okay. So that becomes a limiting factor because then there's only so many police that you can bring in to ship your loads, and the state will only send you so many or allow you to do so many. So they would allow us to do about 3 or 4 a week. So when we were looking at the job, we had to look at these discrete pieces and see, well, how many are super loads? And in fact, I'll show you a graphic, but that is the thing that drove our schedule. Because the Tappan Zee, you know, I told you they're on schedule, but they really wanted a lot of steel. And we said, well, you're going to get it. You know, sometimes contractors say that and then they can't take it, and that becomes a problem. But Tappan Zee did a good job, and they wanted the steel, and we delivered the steel. But then we had all these pieces, and we could only send 3 or 4 a week of the big ones, and there were 290 of those loads. Okay, so 3 or 4 a week divided by 290. So once we got started with those super loads, they were going every week for about a year and a half.
Oh my God.
Okay, but we had to do it to make schedule, which I'm very proud to say we did. So here's a pretty typical span, 12 foot deep. So you look at the size of the guy here, right? Tappan Zee came up with this scheme for putting sections onto the pier. You see there's a lifter here.
Right.
Okay. What they wanted to do to win the job was reduce labor costs, which means you wanted to work as little as possible above the water. You pay an iron worker above the water in New York City premium, right? So they said, well, how can we reduce that labor? So what they did was assemble the steel elsewhere and lift it into place. So the cross section of the bridge, first of all, had 5 girders. You see 1, 2, 3, 4, 5,
Right.
12 foot deep. This is on 19 foot spacing, okay? And then you see the cross frames. Now typically when you see those frames are there to keep the girders stable until you put a deck on. Most bridges, once there's a deck, you could take the frames out, it would be fine. But you need them to erect. And you also need them if you're going to replace the deck later, which typically is done in the Northeast where we have salts tearing up the concrete, right? So it's simply leave the frames there. Here, you'll notice though that there was a substringer, a little smaller piece here. You know, if you think about how the girders are spaced on a bridge, you typically see about 8 or 9 feet, maybe 10 feet. The further you go, the more that concrete has to do in bending. So it might have to get thicker. At 20 feet or 19 feet, you'd have a super thick slab on this bridge. So in order to avoid the span, they put a substringer here to hold up the deck. So we ended up basically delivering 3 pieces on this bridge. Girders, cross frames, and these substringers. Okay. So they had these 5 girder lines, and you see here there are 3. They had a pre-assembled section of 3. Next to it they had a pre-assembled section of 2. And a key to them, this company, or Tappan Zee Constructors, winning the bridge was this crane. I mentioned that bridge in California. They had used this crane in California, and so they had it. They said, hey, we'll bring it, we'll use it to help us on the bridge. The crane is about the height of the Statue of Liberty, okay? It has a 1,900 ton capacity. You know, I think a Volkswagen Beetle weighs about a ton. So about 1,900 Beetles you can pick up with this thing at one time. So massive crane. I mean, here's a tugboat, right? You can't even see the guys who are standing on this thing. So giant, giant crane. So they knew what they could do was put the steel together elsewhere, pick it up, and set it into place. And that's what you see in that other picture with those three
How'd
girders.
they bring that around?
Panama Canal. In fact,
Really?
if you, I'm going to show you, there's a website. If you go to the project website, they have all these clips, and one of them is a story about how they took the crane through the canal.
Oh my word.
And actually, they first took it to New Jersey because they had to replace all the cables, and it cost them like $2 or $3 million
Dude.
just to get the crane ready to do the lifting on this bridge. They renamed it. It was called something else. The Left Coast. It was called the Left Coast Lifter when it did that bridge in California, and now they call it I Lift New York.
I see it up there.
I kind of prefer I Lift New York personally. So here you see it in action,
Oh, there you go.
and this is what they did: groups of 3, groups of 2. There's a fixture here that grabs the steel in just the right places. If you can see it, there's these little hooks that we provided, lifting lugs, they call them, to grab the steel and lift it into place. These units weighed about 1,200 tons.
Wow.
Okay, so the crane had much more capacity than they needed. They did debate, could they get all 5, you know? But they said, no, you know what, that would just be pushing it, that would really be pushing it too far. They decided, they went with 3 and 2, okay? So we sent the steel to Coyman's Point, which is near Albany.
Oh.
So that's 2 hours above the bridge, because Tappan Zee Constructors, that's our customer, decided they would pre-assemble the steel, and they needed some place to do that. Well, real estate in New York City area, number 1 is pricey, number 2, there aren't a lot of big open spaces. So they looked around and they went all the way up there. So when we delivered our steel, and of course we knew when we gave them our bid, we took it past the bridge, a couple of hours up the road where they would assemble. And they really had this amazing facility. There's this sort of underground track you can see here, and there's another one on the other side. And what they had was these little dollies that rode underneath. And so they have these frames, they put the steel together here, and then the dollies come up, and then they go down and they set them down here. And here they would do bolting and put other utilities inside. Then they pick them up and go down, and then they would do the paint, touch up the paint. You'll notice that we paint them, but then you leave the splices unpainted, only the primer. Once you've bolted the splices, you come back and you put the painting on. So they didn't want to do that on the bridge where it's expensive, so they did it in the yard. So when the assembly's ready, they take it out over the water, they bring a barge underneath it, they empty the barge of water, the barge comes up, takes the steel, and then it floats out. And then they float it down the river. Pretty clever, right?
It is clever.
Yeah, these guys know what they're doing. So yeah, here you see going down the river. That assembly is about 400 feet long, probably. 3 girders on that one. 3 or 2. And then that, let's see, same picture we saw earlier. They would come down and they would lift it into place. So our steel went from our plants in Lancaster and Williamsport up to Coyman's, and then they came back downriver to the bridge. Most of the girders we did in Williamsport, we have larger cranes there, and these are big girders. All of those substringers and the cross frames and some of the girders, just a few of them, were done in Lancaster, which is our headquarters. Okay. All right. So here's the plan of the bridge. These are the approaches, and the blue is the main span. When we bid the approaches, the main span wasn't ready. Okay, so they asked us for a bid on the approaches. There are, you see a unit number, unit 1, 2, 3, 4. There are 20 approach units on this project. Okay, And so you see this one here, 1, 2, 3, 4, 5 spans in that unit, 5 spans in that unit. Standard 350-foot spacing. Okay, so try to standardize, to economize as much as possible. All right. So they said to us, "Oh, give us a price for some of these units." And what the Tappan Zee constructors wanted to do was split the steel up around the country as much as they could. And because these units are discrete, they knew that they could get different suppliers. Of course, we wanted as much as possible.
Sure.
We didn't want to split it around, right? So we talked to our biggest competitor, the bad guy, Hirschfeld, and not really the bad guy, especially because Sam is filming this. And we said, hey, you know, we know how much tonnage capacity there is in the United States in girders. So let's go together and tell them we'll do all of the approaches or nothing, all or nothing. And it was a little bit of a risk, you know. What if they say, oh, well, you know, we'll go talk to everyone else to get better prices? We figured that now they won't be able to do it. The kind of schedule they wanted to do, they were going to have to work with us. And they looked and they tried to put it together. And they came back and said, you know what? Okay, you guys got the job. So High and Hirschfeld did all of the approaches, all 20 approach spans. We did 10. They did 10. We did these green ones. They did the red ones. Later, Can-Am, used to be known as Structal, did the main span. Okay, so someone else got that. Although we did end up helping them. So our work was 10 of the 20, 50,000 tons. Okay.
Wow.
That's the largest job in the history of high steel. And in fact, that's why I got involved. My job there is, I'm Vice President of Technical Services, which is usually over quality, and I used to be over engineering. But because it was our biggest project ever, we wanted a little extra sort of executive leadership, and so I was asked to lead this project. So I got to do it.
Good
So
for
that
you.
was,
Wow.
it was a really nice
That is
opportunity for
impressive.
me. Yeah. 528,343 shop man hours. Okay. So if you look at what our capacity was, I told you earlier, it's around 600,000, right? So that was almost all of our capacity for a year, except of course we worked on it for a couple of years. So for a couple of years, it was touching half of our capacity, which is another reason why it had to really go well. You know, of course, if we put a job in the shop, we say, all right, we're going to commit half of our capacity for 2 years. That means there's other stuff that we're not going to take. So if Tappan Zee were to tell us, oh, you know what, High Steel, we're not ready. We'll just call you in about 9 months. Well, now we don't have other steel to put into that shop, right? So we held them accountable. Of course, they wanted their steel, so they held us accountable. Contract negotiations went on for a long
I bet
time.
they were interesting.
But we reached agreement, and it's easy to look back now and say it was successful. But of course, there's a fair amount of risk out there to make sure we got it done right.
Sure. My God.
Is the main span higher than the original?
Yes, they're not higher. I couldn't tell you by how many feet, but they are. So this is our shipping schedule. The blue are the girders. The dark blue are the super loads. So you'll see if you run them together starting in November, late November of 2014, they run, the dark blue lines run together because we had to keep those super loads going, okay? And then of course the red was the stringers and the pink was the cross frame. So it wasn't hard for us to get those up to Coymans, but the other pieces, those super loads, we had to really keep moving.
Well,
Yeah, a few things. We detailed this job in-house. If you're a bridge fabricator, you need shop drawings. Fabricators will either go to sublet detailers or do them in-house. We were debating that, the project this scale, but we did do that in-house. One thing that was unusual with the girder design, when you change thicknesses on your flanges, the designers always change them down. Okay, that gives you a constant parallel web, although there's camber, so it does this. But if you had flange thicknesses that change up, well, then you have to cut your web to fit the flange, which you can do. I've seen it in Europe. I mean, you could do it, but it's not done here. So our software was designed around a constant top of web line. We've used that software for about 30 years. Well, we open the plans, and what do you see? You don't have a constant top of web line. Now, these are field splices, okay? So there isn't a thickness change and individual pieces that we had to worry about. But we did have, our software wouldn't work because our software says constant top of line and we didn't have one. So one of the first things we had to do was rewrite our software. And when that schedule was coming out, we said, well, that software's got to be ready when we bid the job. So when we were getting close, we had to decide, hey, how confident are we going to get that we're going to get this job, because we're going to spend 10 weeks, 2 guys, about 10 hours a day rewriting that software to change that line and making sure that it's right. You don't want to put a bunch of drawings in the shop and then you get steel in the air out on the Hudson and say, oops, we had an error in the software.
Oh, geez.
So these little things that we had to work through, but we did it, and you know, it was fine. Total of 3,028 shop drawings on the job. Now that's just the final approved. Each one went through 3, 4, 5 submittals. Total number was somewhere in the 10 to 15,000 drawings that we sent to them.
Wow.
Just to do the project.
Good heavens.
One of the clever things we did was some capital improvements. It's normal in highway construction for a contractor to get mobilization, okay? So they, right up front, they need money so they can prepare the site, get their equipment in and whatever. Fabricators only get paid on what they do, but we knew to execute the job we were going to have to make some improvements. So we said, okay, we're going to need $10 million up front so that we can retool. And they said, yeah, okay, you know, and that was in our price. So we used the money to improve our plant. So now we have some additional capacity and equipment that's going to help us on other jobs too. So that really was a nice thing. Some improvements to the building, some drilling equipment, improvements to our blasting equipment, cranes, etc., etc. So that was a nice thing for us at the start. Some special processes. We went to digital RT. We shoot x-rays. If you do a 3-inch flange with film, it'll take you about an hour and 20 minutes to shoot that film, okay, depending on the power of your source. But with digital, you can do it in about 12 seconds.
Wow.
So we said, you know what, most of the owners now will let us do digital. New York was not for it. But we told them, hey, we're going to make the schedule, we're going to have it. And so they said, all right, we want our bridge badly enough, we'll let you do it. So we got special approval for digital RT, for drilling, painting. There was a few other things that we got. One that we wanted, electroslag welding, they wouldn't approve. But there are a couple of key things that we got to help us move. I'm trying to go quickly for our schedule, but if you have questions, you can ask me. So here's a drilling gantry we bought.
Wow.
Okay. This is a 12-foot deep girder. So that is a pretty giant opening.
Sure is.
Our traditional way of drilling a hole, the very old process, you would use a small hole, subsize, put your girders together, put your plates there, and then ream them. So you would take them all to the yard and then ream all those holes. Well, you're drilling twice, right? And you're moving girders to the yard so that you could ream it. There's a lot of hours in that. So we have gone to different processes that allow us to drill one time. We do it with a lot of accuracy, but most of those holes are done with drills where it has an arm and you pull it down, okay? Pretty time consuming, okay? Especially if we buy Dillon's high performance steel, because it's great, it's stronger, but it's harder. It takes longer to drill, especially for a guy who's running a hand. So the first girder like this that we drilled, we did do some with the old hand process, and it took us 2.5 shifts to finish a girder, just drilling the holes, okay? This machine here drills all 3 plies and can do them all at the same time, okay? So we could finish an end of a girder in about 2.5 hours compared to all those shifts it takes, because it's just got so much power and it just goes, okay? So that was one of the nicest pieces of equipment we bought for that project.
Now, is that something you own, or do you have it just for this job?
We own it, yeah.
Oh, wow.
We already had one that was smaller in Lancaster, and we bought this one with that money we got to do the project on Tappan Zee.
How do you cool the metal while you're drilling it?
You spray it with coolant. There's a coolant fluid. It's not an oil because you want it to get off of there. It evaporates. Yeah, but it makes a mess. But you know, you've got to keep it cool. It's a good question. Number of holes. So these are the bolts. 465,000 bolts on our approaches, right? That's not Hirschfeld's approaches.
Oh my God.
And of course, every bolt is joining splice plate, flange, splice plate, maybe a fill plate in there. Maybe 1.4 million holes we
Oh,
drill.
my word.
So was it a good idea to buy some faster drilling equipment?
You better.
Yeah, I think it was.
Paid
Right?
off.
Yeah. Okay.
Yep.
And here's that digital RT. The guy puts under this platen, and then you get the shot here. Of course, digital is normal for all of us. When was the last time you went to a doctor and he showed you a piece of film? Right. It's right there. And the bridge industry, if you're doing a New York bridge, they still have film. All the other owners it's a long story. All the other owners will let us use digital. Okay, and it's fast. You shoot it, and then you see. If you have a problem, you know. If you're doing film, you take the film, you take it back, you develop it, you make sure it's clean, then you look at it, oh, we got a problem. It's 2 hours later. So, not that we have problems very often, but if we do, then we want to know. So digital RT came in. So here's the girders, pretty straightforward cross section. Most of them look like this. These are jacking stiffeners. One of the things that the owner will have to do over the life of the bridge is replace the bearings. So if you go to the piers, what they'll do is they'll go on the pier, they'll put a jack under there and they'll lift it up and they'll take the bearings out. Where the bridge is continuous over the pier, they can just use the framing. But where there wasn't room where those units stop, so you might have noticed in that picture there was a wider stiffener like this. That was so they could jack up and replace the bearings when it comes time to do that. So 793 girders, 76 done in Lancaster, and the rest of them done in Williamsport. Okay. Cross frames, 2,852 cross frames, all done in Lancaster, and much bigger than usual. Here's a guy welding. We had just bought a robot before we got this job. Okay, so that the robot goes around and does the welds. And when we bought it, your trade-off, right? How much space do we need? How big does this robot need to be? We looked at our population of frames. We said, all right, here's the size we should go. That'll cover 95% of the frames we've ever seen. 6 months later, we got the Tappan Zee, and the frames were too big to use the robot. So, we didn't luck out there. But we knew we'd have to weld them by hand, and it was in the job. And we did fine with that. But it's too bad. It would have been nice to use that robot. So these are those substringers. I showed you those little pieces that sit on the frames. And you also see the paint here. This is the primer, has kind of a green look. There's an epoxy intermediate, and the epoxy binds the urethane. And of course, the urethane has a color on top. So here you see the bridge. This is today, October 19th, 2017. Wow. Okay? So you see the old bridge here.
Yep.
The old bridge is closed. That's kind of too bad, because when they were building the new bridge, you could really see the steel if you drove on the old bridge. Did anybody drive on the old one while they were in construction?
Oh, yeah.
Yeah, that was nice, right? Except watch,
So the old bridge is closed now?
The old bridge is closed as of about, I think, 2 weeks ago. In fact, they had a thing in the news, a guy in an old car, I didn't see what year it was, 1930s car or something, 50s maybe, drove across the bridge. Yeah, so this is the westbound lane, and this is the eastbound lane.
Right.
So the new bridge is double the width of the old one, see? Here's the old bridge. So what they did was they finished the westbound first.
Oh my gosh.
And they moved all the traffic, first the westbound traffic and then the eastbound. So all of the traffic is on the westbound bridge.
Oh.
Because in order to tie in the eastbound bridge, you still see there's no concrete here. They have to destroy the old bridge, okay? So they staged it that way, okay? So now you got all the traffic is all on the new bridge, but it's all on one lane. They're not telling us the exact date, but I'm going to say sometime in maybe late summer or early fall next year they'll open the whole thing. So then the project will be done.
Wow.
But that's my estimation. They are not saying. They don't want to say.
It's beautiful at night the way they have those blue lights on there.
Yeah, very attractive structure. You still see the I Lift New York. And they're going to bring it over here when they needed to put those sections in. So just a few final things. There is a website that is really good. If you want to see more information about the bridge, like that picture I took was from the camera. webcam, you can easily search new New York Bridge, and it'll pop up. If you want the URL, it's newnybridge.com. For a long time they didn't have a name. It is now the Mario R. Como Bridge. Is that the middle name? Mario A.
M.
M.
It's his son.
Yeah. The bridge is named for the father. So I thought, well, the governor named it for himself, but actually he named it for his father. So it's named after his father. So let's see, real quick, if we go.
I hope ArcelorMittal is gonna get the scrap of the old bridge.
What? Yeah, I'm sure Dylan's licking his chops, seeing all that steel out there. So here, we won't take any time with it. I know we're short on time, but if you were to go to the website, you would go and you could. I took you where the webcams are. So here's they take a picture every 15 minutes.
Oh, really?
Okay. So if you go down here to the bottom, let's see, where are we? Oh, it's not, okay. Yeah, okay, here. You see there's October 11th, 2013. So if you go to that website, you can click at any point in time, and it'll show you what was going on at that time, every 15 minutes. So you could make your own little clip and look at the life of the bridge as it went. So here, that was, April 2015, that's what it looked like, right? So, and the other thing I'll mention in terms of the webcams, there are about 6 of them. I think where I am is the Rockland. You can go to the Westchester, the other landing, and so you can mosey around. Over here, there's also videos and photos. And so I'm going to go back one other thing to show you before we go. They recently released this clip, 4 years and 2 minutes.
No kidding. Wow.
Okay. Oops, sorry guys.
That's impressive.
Really is amazing. All the barges, all the guys out there.
That's amazing. What are those tall towers over there? Those huge towers.
These?
What are those?
Oh, well, they had concrete plants out there, but here, this is where they're building the main span.
Right.
Yeah, 350 foot, you just use a typical pier, but for that long span, you have the cables that come down. You see the steel approach coming.
Right.
The other thing about those cables is it's really good for erection. You just go section by section as you work your way out.
You said $5 billion
Pardon?
project? How much was the project cost?
3.98 billion.
Really? That's amazing how they did that. Yeah, I know.
These guys really knew what they were doing.
Oh my gosh. So that's the new entrance. Wow, that's beautiful.
Nice shot with the moon there and everything.
Yeah.
Okay, exit now. So, that's all I had.
Well, I'll tell you, great job.
Oh, thank you. Thank you. I think
All the way around.
that'll, yeah, those clips are still running in the browser over there. Are there any questions? I know we're short. Go ahead.
Couple of quick ones.
Yeah.
Do you know why they didn't put tracks across the bridge?
I understand it was a question of cost. You know, they did design it for rail capacity. So I showed you how wide it is. They can add a rail later, but they didn't want to spend the money on that up front. So that might be later. Yeah.
And are you familiar with the Tacony, Washington State Bridge that crashed?
Yes.
What happened?
Yeah, the Galloping Gertie.
Yeah.
Have you guys seen that? Probably you have. I mean, we could pull it up pretty quickly. There was a bridge. It was a suspension bridge, late 1930s, I think, and it was a harmonic motion from the wind. And what happens is when the wind hits your structure, if it catches it just right, depending on the resonant frequency of the structure, it can oscillate. Similarly, there's a bridge in Texas that it's cable stay, and when the wind's blowing, they stay still. If there's a hard rain, they stay still. But if there's a light rain, the water comes off just right, and the cables bounce. And what they had to do is tie them together to change the frequency of those things. Okay? Well, that's a scale on some cables. This bridge, it was a Tacoma Narrows. You can search Galloping Gertie, and you'll see the clip. And it's a suspension bridge, right, between two beautiful areas there. And the wind hits it, and it accelerates, and it does this cable stay bridge. And it's actually kind of interesting how flexible the steel is. I mean, it really took it for a long time. Finally, the whole thing comes apart. You know, there's a car, like a Packard or something, sitting on the road there. Yeah, so they rebuilt it. But now, whenever you do a long bridge like this one, anything of that length, you'll do wind tunnel testing on the model of that bridge. It's a good question. Yes?
Is there a pedestrian walkway?
Yeah.
Bike lane?
Yes, there is. That's interesting. That's a 3-mile hike, right? But I know we provided, what do they call them? It's a B word. I think 3 places along the bridge, some steel framing that comes out because they want a little viewing area so you can walk out. So I know there's a path on the whole bridge and then a couple of places where you can stop and whatnot. But it's a very wide walkway. Yeah. Question? Go ahead.
We have a congestion problem on Route 30 between Coatesville and Darrington. And I was thinking, I got a 10-mile bridge for you.
Okay, let's talk. 10 miles. Let's see. $4 billion, 3 miles. So, but we don't have to put piers in the water. We can make a deal. You had a question?
Last year there was a crane accident.
Yeah.
Tappan Zee. You know the story of that?
Oh yeah. What happened? What happened?
Crane failed and fell. I think it went overboard.
Yeah, and in fact they were lucky because it came down on the road and it didn't hit any vehicles. Oh, I forget. I apologize. I remember there was they had 2 incidences. They don't like to talk about it, but there was a crane that came down, and they actually early in the job lost a cement plant or concrete ready-mix plant. So they had 2 of them out there on barges, and 1 came over. Yeah, but I will tell you, I'll give them very high marks for safety. You know, it's old bridges. You'd count the fatalities, right? There wasn't anything like that out there. Very, very, very safety focused. In fact, they pulled us into that safety discussion.
Oh, good.
Yeah. You have a question?
How many people were working on just the bid, and like what was your timeline for the bid?
Yeah, for us. God, let's think back about that. We would have had probably 3 people. Now, here's the interesting thing. It's a design build. So a traditional job is design, bid, build. We get the complete design. So we're only estimating it once. But a design, bid, build, it's competition. So we have to give prices to anybody who wants one, and you know, we try to bid them all. So there were 3 people. Actually, I said there were 4. So we ended up giving numbers to 4. So we had 3 people working on those 4 bids. Weeks, how much time? Yeah, that's a good question. I couldn't really tell you, but yeah, it was a fair amount of time.
Okay, but you had a good span of time to really look at the plans and
yes,
things,
yeah, we did.
Coming together?
Yes, we did. And in fact, what happened was this: there were those 4, and then one of them just dropped out. I mean, it's weeks before. So those 3, and we had given them preliminary information, and what we call it is a budget price, because they're going to refine, right? And we're not going to commit to that. So then Tappan Zee Constructors won the job in I want to say it was either late 11 or early 12. We didn't sign a contract till 2013. So they won the job, and then they put 4,000 designers together to finish the design, okay? And so then they started feeding the suppliers information so that we could work on a bid. But at that time, we only had to refine one. So we had plenty of time. And one of the other things to note about that, lots of girders, cross frames, stringers, a lot of repeat. So it wasn't that hard to bid because you had a lot of the same thing over and over. That's a good question. Yes?
Who's taking apart the old one?
I don't know. There's not a contract there yet. Those old bridges, they either blow them into the water or they take them apart. And here, I've heard they've decided they'll have to take them apart. But that'll be a contract for someone else. I guess the Thruway will let that. Soon, probably.
Hope it stays domestic.
Yep. Yeah, who knows? Yeah, who knows? Yes?
Tappan Zee Constructors, were they just a company formed to do this job?
Yeah, they were made of quite a number of the larger companies. Fluor, you may have heard of Fluor, and American Bridge. American Bridge was originally based, it was part of U.S. Steel in Pittsburgh, right? It became U.S. Bridge. They're still out there. So American Bridge and Fluor were the leading contractors. Then there were some other smaller ones like Granite is another one. HDR was a designer. Okay, so HDR, Fluor, Granite, those, they put a consortium together and called it Tappan Zee Constructors. Yeah. I saw another hand. Anyone else?
I bet the tolls are going up.
Yeah, they haven't published a number, but I thought I heard somewhere like from 5 to 15 or something like that.
Okay.
Yeah.
To make it easier, you make it electronically now.
Oh, yeah.
So you don't have to pay the money.
Yeah, that's modern toll bridges. They don't have toll booths anymore because it costs too much, right? Although a lot of times they'll have a small one on the side. So, if you want to get off, you can pay a toll. But mostly you'll use a tag and just go through at highway speed.
Yeah. They have a beam right on top of you, drive under it.
Yeah, that's right. Which is nice, because who wants to slow down at a toll booth?
You did a great job. That was
Thank you.
Fantastic information.
Yeah, well, and thank you guys for having me. It was
thank you for
my pleasure.